Hello everyone, today we will solve some problem based on inner product space. And some previous concepts. So first problem is this T is a operator on R7. Now the question is nilpotent operator, that is of index 4, that means T to the power 4 equal to 0. So from here we obtain the minimal polynomial. Index means lowest degree of lowest degree n such that T to the power n equal to 0. So minimal polynomial of this nilpotent operator, it will look like x to the power 4, because we know for nilpotent operator only eigenvalue is 0, therefore minimal polynomial must be of this form, right? X to the power n, and here 4 is the lowest degree polynomial for which this equation is satisfied. Therefore the minimal polynomial of this will be x to the power 4. Now we need to find Jordan canonical form using those two data. That is, minimal polynomial is already given, and another data is nullity is already given. So from nullity, what can be concluded? Since nullity is 3, nullity
So C.
Yes. So nullity is 3 means there will be 3 blocks, right? There will be 3 blocks like this. So we need to find Jordan canonical form, and we already know from nullity is 3 because we know that for each blocks the rank is 1, because those diagonal entries are 0 here. So those each blocks
So C.
has a rank. Yeah. So let us see what is the option, correct option. So minimal polynomial is x to the power 4 means Jordan, there exists a Jordan block of size 4. Right? There exists a Jordan block of size 4. So only C contains the Jordan block of size 4. And the rest of the thing is already determined, right? Because this is the Jordan block 0, 0, 0, 0 and 1 above. Now rest of the thing, there are exactly 2 Jordan blocks. So 2 Jordan blocks means it is 7 by 7 matrix, so there should be 4 entries. So let me put those 4 entries. Now sorry, there should be only three diagonal entries. Now 2 Jordan blocks means we have only one choice, that is one Jordan blocks is like this and another is the single entry. So option C is correct. Okay, your answer is right. So now let us solve the question number 2. Here the vector space V is R2 and inner product is already defined. We need to see if what is the condition such that those two are orthogonal. So let us recall that inner product. What is the meaning of inner product? Inner product means it is a map from, given a vector space V, then we define a map from V cross V to the scalar field F, right? So it satisfies some property, and the notation is V comma W to inner product between those two vectors. V comma W, for example, here it is given as alpha comma beta, and it satisfies some property like some alpha plus alpha dash comma beta, so that is same as alpha comma beta plus alpha dash comma beta. And there are similarly, if there is some C, then just put take C out, take C common. And similarly for the other part, the similar thing actually holds. But there should be some conjugation. For example, alpha comma C beta, this is same as C times alpha beta, C bar. We need to take C bar here. Okay. So those are some property. Another thing is like alpha comma alpha, this inner product is 0 if and only if alpha equal to 0. So those kind of properties should be satisfied. So it is generalization of usual dot product. You already know dot product. This is just generalize that dot product thing. And now here alpha comma beta is defined as this. So alpha is x1 comma x2, this tuples, and beta is also this. Now we need to take the inner product. So orthogonal means alpha comma beta, those are alpha is said to be orthogonal to beta if and only if this inner product actually 0. So let us find the inner product 2y minus x and x comma y. So by definition this is same as first multiply first two components, which is 2 times 2y times x, and we multiply those last two components. It is minus x.
Option B.
Okay, so let me check. Then minus 2 x1, that is first component 2y times x, 2y times y, and then minus 2 times minus x, and then again x. So this is same as 2xy and minus 4xy. So there will be there will be only single xy terms, and now there is plus 2x square and minus 4y square. So this is 0. So given that, so we need to find a condition such that this equal to 0. This is 0 if and only if x, just solve this quadratic equation. It is same as minus b. Is there something wrong? Two y times x.
But there should be minus 5xy.
Yes. So I have done something wrong maybe. 2y times. Okay, so let me check.
But there is minus 5xy by term, sir.
Thank you.
The second term is, sir, minus 5xy.
So 2y, oh yes, you are right. Second term will be minus 5xy. 5 times minus xy. By definition, right? Okay. So from here we obtain the equation will be like this.
3x minus 3xy.
Minus 3xy. And just using that quadratic formula, we know the solution. This is equal to 0 if and only if that is minus b, which is plus 3y, and we are thinking this as a quadratic of x. Okay, we are treating y as a constant. So 3y plus minus root over b square, which is 9x square, minus 4ac, which is 32y square, by 2a, which is 4. And this is same as 3 plus minus root 41y by 4. So option C is the correct answer. Sorry, option B. Option B. Yes. Okay. Now let us see question number 3. Here it is given that, so it is actually R4. V is R4, and the linear operator is given by this equation. Now alpha equal to minus 1, these 4 tuples, we need to see what is Z alpha t. Z alpha t means it is the subspace generated by any polynomial of t applied on alpha. Okay. So let us see what will be t applied on alpha. So by definition, we can see that t of x1, x2, x3, x4. Just do something like this. So first one is x1 plus x2 plus x3. So let me put the sum. Let x1, x2, x3, x4. That sum is uh, s. Let s is same as sum xi. I equal to 1 to 4. Okay. So first one is s minus. There is 4 missing s minus x4, then s minus x1, s minus x2, and s minus 1 to 3. 3 is missing. So this is the transformation. Now, so if we put the value for this, we know actually this there should be s of x, which should be denoted by some sx. Okay. So for alpha, we have the sum is actually 0, right? Okay. So for alpha, this will be t of alpha, because what is minus 1 plus 1 minus 1 plus 1? This sum is 0 for alpha, right? Therefore, this is 0 minus x4. x4 means fourth component, which is minus 1. Then again 0 minus x1, which is minus 1. Then 0 minus x2 and 0 minus x3. x2 is, yes. So 0 minus x3. x3 means minus 1. So this is minus 1 plus 1 minus 1 plus 1, right? And we can see this is actually same as alpha. Therefore, whatever polynomial, maybe whatever power we take, if we compose multiple times, this is actually identity operator, right? Not identity operator, but t acting on alpha, it acts like identity. So t to the power n alpha, this is same as alpha, just compose n times. And therefore, any polynomial, if we take any polynomial, that is, any polynomial will look like some c to the power I, t to the power I of alpha, sum of this thing, I equal to some 0 to maybe n. So maybe we denote it by t to the power I. And we obtain that this is same as c to the ci, sorry, this is coefficient, so index is lower. So ci ti alpha, which is same as alpha. And this is same as actually alpha. We, yes. So ft acting on alpha. Sorry, what is the problem? T to the power I alpha. Yes. So sum of ci alpha means it is just take alpha common, then this is actually sum of ci into alpha. That is ft alpha. It belongs to the span of alpha, right? Span of this singleton vector alpha. Therefore, from here it is clear that dimension of this z alpha t, this is actually same as dimension. It is actually generated by alpha, right? So dimension of this thing, dimension of z alpha t, this is actually one dimension. So this is the correct answer. Is it okay?
Sir,
Yes.
but can we say that the dimension of this subspace cyclic, actually this is defined as cyclic?
Yes. This is called cyclic, maybe cyclic space or like this.
Yes, sir.
Yeah.
Generated by alpha.
Yes.
So can we say that the dimension of this subspace is actually equal to the rank of T?
The length of
Rank of T.
no, that is actually dimension of this z alpha t. That is actually same as rank of the minimal rank. So suppose p is a polynomial which annihilates this alpha. P is a polynomial of t which annihilates. So suppose px is a polynomial which annihilates this alpha. That is, p of alpha is 0. Okay. Then the lowest degree polynomial, sorry, pt. So the lowest degree polynomial actually gives dimension of this z alpha.
So minimal polynomial, actually the degree of minimal polynomial is the dimension of this cyclic space.
Yes, not minimal polynomial actually. This is all such polynomial which annihilates this alpha. Not
Degree we can say na, we can say the degree, sir. Because
yes,
the minimal degree poly.
yes, minimal. Yes, you are right. Minimal degree polynomial, but it is not minimal polynomial. Okay.
No, I am not saying that minimal
Yeah.
polynomial, but I am saying the degree of the minimal polynomial.
Yes, degree of minimal polynomial. So you can see that this is actually degree of. So you can see T alpha is same as alpha. Therefore, T minus 1. This will be the minimal polynomial. Because any 0-degree polynomial, you cannot annihilate this alpha by 0-degree polynomial. So T minus 1 alpha. So from here you can also conclude. That is T minus 1. This is the, so here the degree of the polynomial is 1. And so this should be the minimal polynomial. Is it clear? So from here also you can conclude.
Sir, how can we prove for general cases, sir?
In general, either you need to find those kind of minimal polynomial which annihilates alpha, but otherwise it is better to just see what happens when you apply t on those alpha and just write those kind of sum and see what combination it can be. That is how we can solve.
Sir, can we say that the minimal n such that Tn alpha is equal to alpha is the dimension of this space?
No, you cannot always say those kind of, because Tn alpha may not be same as actually alpha. That is a problem. Yes, this may not be same as alpha.
But whenever this is, then we can say this. Whenever this kind of things happen, sir.
T to the power I alpha is same as alpha. It may not actually possible. It may not possible always. There may
No, whenever it is possible, then we
yes,
can say that.
whenever possible, then you may conclude. Uh, then also yes, then you may conclude.
Because then for higher degree, sir, it will become alpha, sir. I
Yes,
think.
for a higher degree, those are completely determined. Yes, then you can conclude. Then you can even prove those alpha t alpha up to those t to the power I minus alpha. Those are actually basis of. Those actually generates this z alpha t. Yes, you are right. Okay, so let me solve the next question. Here, the operator, sorry, it is not operator, it is a linear transformation from P to R. P to R means polynomial whose degree is at most 2, and T is the linear transformation defined by this. And we need to see, it is not norm, it is actually inner product. We need to see inner product induced by this T. Okay. So what will be inner product? So what is inner product induced by T means? So suppose P is a polynomial. Okay, P belongs to this P to R, and Q is another polynomial. Then the inner product of these two polynomial P comma Q, this
T of P, comma T of Q, inner product.
yes, it will be defined by T of P comma T of Q, because we already know what is inner product in R3, right? Just multiply
Q and T is injective.
uh, so suppose for Rn we can define inner product by this formula. Just take two n tuples and take the sum of AIBI. In general, for Cn we need to take conjugate. Okay, so this is how we
But T should be injective, na, sir?
yes, T should be actually T belongs to GLNR. This is one of the conditions. T should be invertible. Only injective is not So if dimension is same, then injectivity is same as isomorphism, so it is okay. So this condition should be needed. Otherwise,
Because then positiveness will not be satisfied for non-zero. For
yes,
non-zero vectors, this will be zero.
yes, because we need those conditions. X comma x inner product is 0 if and only if x equal.
X is zero. Yes.
This kind of condition is not always true. This will be only true when those are GLNR.
Yes.
Those are invertible. Those transformation are invertible. Okay, so let p equal to this polynomial. So let px equal to this polynomial a0 plus a1x plus a2x square. And similarly qx equal to this b0 plus b1x plus b2x square. Then using so TP, what is by definition TP is same as A0, A1, A2, and TQ is same as B0, B1, B2. So this is actually using this definition inner product in Rn. This is same as A0, B0. Sorry, sum of those things, that is A0, B0 plus A1, B1 plus A2, B2. And now we need to express in terms of actually p. We need to express those in terms of this derivative and double derivative. So we can also see that p dash x first derivative, this is same as a0 plus a1x, and p double dash x, sorry, this is
Options
a1
C,
plus,
sir.
yeah, a1 plus 2a2x, and p double dash x, this is 2a2. So if we put the value 0, then P0, from here we can see P0 is same as A0, and from here P dash 0 is same as A1, and from here P double dash 0 is same as 2A2. P double dash 0 equal to 2A2, so A2 equal to this by 2. Yes.
Option C is correct, sir.
Yeah. So if we put here all those values, then we get this is same as P0 times
0
Q0
to 0
plus
plus
P
1
dash
by
0 Q dash 0 plus P double dash 0 by 2 into Q double dash 0 by 2. So those are 2 into 2 means 4. So option, which option is correct? This C.
A.
Sorry, A. And such a norm, it is certainly exists. Such a inner product always exists. So this is the inner product.
Sir.
Yeah.
Sir, P dash X is A1 plus 2A2, na? 2A2X.
Yes. So if you put
So
0,
P dash 0, so we'll get A1. Okay, sir.
okay. So let us solve the next question. Okay. So here V is actually R3, and the basis, this is the given basis. Now we need to apply Gram-Schmidt method, and we need to orthogonalize this basis. So what is orthogonality? So alpha 1 up to alpha n, those are called orthogonal. Maybe write it as beta 1. So those are called orthogonal basis of a vector space if and only if beta I and beta j, that inner product is actually 0 whenever I not equal to 0. Okay, and this is for orthogonality condition. If in addition, if this condition is also holding, that is beta I inner product with beta I, this is 1, then orthogonal plus this condition, those are called orthonormal basis. A basis satisfying those two conditions are called orthonormal basis. So here we need to find orthogonal basis by using Gram-Schmidt method. So what is actually Gram-Schmidt method? So given a vector, given a collection of vector alpha 1 up to alpha n, which is a basis for the given vector space V. Okay, so using Gram-Schmidt method, we can find a orthogonal basis. Okay, beta 1 up to beta n, which are bases, but it satisfy the additional condition. Inner product of beta 1 with beta 2 or beta 1 with beta n, those are 0. Okay, any two, if you take any two different thing and take inner product, those will be 0. So how do we obtain the Gram-Schmidt? How do we obtain those beta 1 up to beta n? So the process is very simple. Take beta 1 is same as alpha 1, then beta 2 is same as alpha 2, but remove the component of alpha 1. Okay, so you take the projection of alpha 1 on projection of alpha 2 on alpha 1. So this is the projection formula, and just remove this part, right? Similarly, beta 3, it is same as alpha 3 minus, now remove projection of alpha 3 on alpha 1. First we'll remove this projection part, and then we remove the projects, so not actually alpha 1, so let me put it as beta 1, then it is more easy to understand. Actually beta 1 and alpha 1 are same, but we write this, and now we remove the projection on this beta 2. Okay, so projection of alpha 3 on beta 2. In this way, the process will continue up to beta n. Okay, so here it is 3-dimensional. Now we need to find the first, second thing, beta 2. That is this thing we need to find. Okay, so again, just copy this page. Okay, so if we use the formula, then beta 1 is same as alpha 1, so write it as alpha 1, alpha 2, alpha 3. Okay, so beta 1 is same as alpha 1, which is 2, 1, 2, and now beta 2 is same as alpha 2 minus, remove the projection of alpha 2 on beta 1. So alpha 2 is, so let us first calculate alpha 2 inner product with beta 1. So beta 1 is same as alpha 1, so alpha 2 means 462 and beta 1 means 212. So multiply component wise, so 4 times 2 plus 6 times 1 plus 2 times 2. Okay, first component into first, second into second, third into third. So this is actually same as 8, 6, 14 and 18, right? This is same as 18. 4, 6, 2 and 2, 1, 2, yes. So, and norm, let us calculate norm of beta 1 square. So norm of beta 1 square, so definition of norm is like this. Just take the inner product with, so this is same as 4 square. Okay, so let me calculate.
Oh, what are you writing? So 2 square plus 1 square plus 2 square.
2 square plus 1 square plus 2 square, which is 9. So this is alpha 2 means 462 and minus 18 by 9 into beta 1. Beta 1 means 2, 1. So this is alpha 1. Okay. So just this is actually 2 and 0. Then 6 minus 2 which is 4, then 2 minus 4 which is minus 2. So 0, 4 minus 2, so this is the correct answer. Okay. Now the next question is the same question, actually repetition of the same thing, but we need to find beta 3. So again, beta 3 is same as alpha 3. This
First,
is
we need to find beta 2.
Yes, beta 2 is already obtained, right? That is the same question. So alpha 3 minus alpha 3 projection on beta 1. Yes. So we need to find those alpha 3 inner product with beta 1. So alpha 3 means 10 to minus 6, and beta 1 means this first one 2 1 2, that is same as 20 plus 2 minus 12, which is 10, and norm of beta 1 square, this is same as, this is beta 1, so this is 2 square plus 1 square plus 2 square, which is 9. Now similarly, alpha 3 times beta 2, this is same as 10 to minus 6, 10 to minus 6 times beta 2. Beta 2 is actually 0 4 minus 2, we have previously calculated. 0 4 minus 2, so this is actually same as 0
Minus
plus
4.
8 minus plus 12, yes, 20. And now norm of beta 2 square, this is beta 2 inner product beta
20.
yes, so this is actually again 20. So let me put those values. So alpha 3 is 10 to minus 6, 10 to minus 6 minus alpha 3 times beta 1, this inner product is 10 by norm beta 1 square means 9 times beta 1 means 2 1 2 minus alpha 3 inner product beta 2, which is calculated 20, and norm square is also 20 minus beta 2 times beta 2. Beta 2 means 0 4 minus 2, so those are cancelled. So this is 10. So let me just take the LCM and multiply. So below, take 1 by 9 common, so it is 90 minus 20 and minus 0, then 18 minus 10 and then minus 30.
436.
Then is it correct? Yes. Then minus 54, last component is minus 54, then minus 20, and then minus 18, plus 18. Okay. So if we just subtract, the first component is 70, then the second component is minus 28, and the last one is minus 56. So 70 minus 28 minus 56. So this is option C is the correct answer. Okay. So let us see question number 8. So here alpha 1, those are 4 vectors actually, and those are 4 vectors. Beta is also given, we need to find coordinate of beta with respect to alpha. So this process is difficult, right? Means there are lots of calculation to find those kind of things. We need to solve this kind of equation. Solving those alpha 1, we take the matrix alpha 1, alpha 2, alpha 3, alpha 4 and put that entry beta, and just we need to row reduce those things, and finally we obtain something like some row reduction, and here beta. From here we obtain those coefficients for which beta can be written as linear combination of those coefficients, right? So what is the matrix of something? So suppose beta can be written as C1 alpha 1 plus C2 alpha 2 plus C3 alpha 3 and C4 alpha 4. Then beta basis of this ordered basis. So with respect to this ordered basis, the coordinate will be C1, C2, C3, C4. So this process is lengthy process into calculate lots of things. But here we just need to observe something. So if we put those, so let us write
Sir,
a yes,
sir,
yes,
sir, the coordinates will be given by inner product of alpha 1 beta, first coordinate, second will be
yes,
inner
you are right.
product.
So let me explain why this is true. So suppose we make a matrix like this, A equal to alpha 1, put those alpha 1 in the first column, so alpha 1 transpose, alpha 2 transpose, alpha 3 transpose and alpha 4. Then this is actually same as half, 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 half. Then those are actually transpose previously also. Then again half, half, minus half, minus half. Then half, half, then plus half, second and fourth. So if you notice this multiplication A transpose A, this is actually identity matrix. Just multiply, take the transpose and multiply. This is identity, and this is also same as A transpose. So from here it is clear that A is orthogonal. So what is the meaning of this? A is orthogonal means just multiply this, multiply this with other things, this will give 0, and multiply this with the same thing, this will give 1, right? Just we have transposed this thing. So if we transpose, A transpose means it will contain the first row. So first row times this, so R1 times this R1, this will be actually 1, right? So norm of these things is 1. Similarly, this times this will give you 0, this times this will give you 0, like this. So A is orthogonal actually means,
Sir, this is orthonormal actually, sir.
yes, this is more than that, it is orthonormal because norm of those things are actually 1. So A is orthogonal. From here we conclude those alpha 1 up to alpha n, here alpha 4, this is actually is orthonormal basis. So something is orthonormal, that actually means beta can be, so suppose beta is same as those Ci alpha I, then we can observe the fact, if you just multiply with some alpha j, this is same as sum of Ci alpha I inner product with alpha j. But inner product of alpha I with alpha j, that is 0
0.
over I not equal to j. Right?
Ci alpha I alpha I.
Yes.
This
So
is
only
the
Cj will survive because alpha I inner product alpha I is 1. So rest of the other things are 0. Therefore, from here it is easy to calculate those coefficients. Instead of doing all those things, that is row reduction, it is more easy to solve because just take inner product with those alpha 1 up to alpha n.
Sir, if it is only orthogonal, so we need to divide by the norm of the things.
Yes, if it is only orthogonal, then it is better to just divide by those norms. So something, for example, instead of half, suppose there is only 1 1 1 1, then divide it by its norm. So norm means 1 square 1 square, which is 2, right? So that's why you need to normalize those things. So let me calculate beta times alpha 1, which will give, by this equation, this will give C1. So C1 is beta times alpha 1.
By 2.
Yes. It will be, so let me calculate the first term. So 1 5 minus 4 3 and half 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 half. So this is 1 times half, that is half, plus 5 times half, 5 by 2 minus 4 by 2 plus 3 by 2. So 6 minus 4, which is 2, plus 3, 5 by 2. So first entry will be 5 by 2. Similarly, C2 is beta times alpha 2, this inner product. And if you calculate, this will be actually
7 by 2, sir.
yes. So this will be actually 7 by 2. So let me put all those things. So the coordinate C1, C2, C3, C4. This is the coordinate of B with respect to this basis. This is actually same as those 1 plus 5 minus 4 plus 3 by 2. We just multiply with sign and divide it by 2. Okay. 1 plus 5 plus 4 minus 3 by 2. And similarly, the other components are 1 minus 5 plus 4 plus 3 by 2. And last component 1 minus 5 minus 4 minus 3 by 2. So those are actually half times 5, 7, 3 minus 11.
Minus 11.
Yeah, minus 11. So this is the correct
B.
answer. B. Okay. So let us solve question number 9. Here you can see real valued continuous function. F is real valued continuous function. So F is a function from R to R. Maybe not R to R, maybe some vector space to R, because it is only real valued, but domain we don't know. Domain is some vector space. Now, which of the following is true? So what we know about inner product? We know something like this. Cauchy squares inequality. What it tells? It tells that
Modulus of inner product alpha beta is less than or equal to norm alpha into norm beta.
yeah. So mod of the inner product, it is
Less than or equal to, sir.
norm of alpha and norm of beta. And moreover, this equality holds. This equality here, less equal to is can be replaced by equality. This holds.
You're linearly dependent.
Yes, if and only if beta is some C alpha. That is not C alpha. Alpha can be some C beta. So if beta and alpha are linearly dependent. Linearly dependent. Okay. So just apply. So first let us define an inner product. So given to such function f and g, so consider the vector space. Let V be the vector space of all continuous function f maps B to R. So this is the vector space, and we can define inner product in this space. So suppose f and g are two function, then their inner product, define their inner product as integration from 0 to 1 and fx times gx bar. So here bar means actually same because those entries are real, but for complex case we define as fx times g bar x. Okay, so g bar x dx. So this is the inner product. We can easily check why this is inner product because it is similar check actually. A times b bar, those kind of same check. Okay, so this is an inner product, and if instead of this g, if we just put x, then what happens?
Sir, option B.
Yes, so let me check what actually happens. So x inner product with f, x means the function which sends everything to the identity. Okay. So,
Sir, we need to only find the norm of x and norm of fx.
yes.
Because in the left hand side we have given modulus of inner product.
So let gx equal to x. Okay. So this inner product, this is same as 0 to 1 fx times gx bar, which is x times fx dx. Right? Now using this Cauchy-Squarge inequality, mod of this 0 to 1 x fx dx, that is left hand side, this is less equal to norm of alpha. So norm of alpha means norm of fx, right? So norm of fx, this is actually same as take the inner product of these things and just take the square root. So by our definition, this is same as 0 to 1 fx times fx, that is fx whole square into dx, right? And take square root of this thing. Okay, so mod fx square and fx square are same in this case, so we just put mod fx. And norm of the second thing gx, again by same definition, this is 0 to 1 mod of gx square, which is same as x square dx, which is 1/3, right? X cubed by 3, which is just put the value, so 1/3. So by Cauchy-Squarge inequality, this is same less equal to mod of norm of fx times norm of gx maybe write it as norm f norm g, because g is assumed as the x, that function, by Cauchy-Squarge. And we have already calculated the first one, norm of f, this is actually same as 0 to 1 mod fx square dx, square root of these things, and norm of gx, this is actually 1/3, so we may put 1/3 here. Sorry, this is actually square root of this 1/3. Okay, I have forgotten here to take the square root of this thing. So this is the answer. So this thing is actually bounded by 1/3 times mod fx square dx. So 1/3. So which of the following is correct actually? So is it correct? So this is we
Yes,
have
sir. This is correct.
we may not No, right? We don't know if it is correct or not.
Why, sir?
Because something is, yes, sorry, this is actually correct. Because something is less than one third means it is also less than half. And similarly, it also less than one.
1.
So one third is less than those two things. So this is correct.
Then A and option B.
B is also correct, right? So those two are correct answer. Option A, option B are correct. But what about option C?
We
Now
don't know.
we don't know if those are correct or not. So we need to check if those are correct or not. Okay. So just take a function and let us see if those are correct. For example, if we take fx equal to, we need to find a counter example to see if those are correct or not. We don't know yet. So take fx equal to x. So if we take this, then fx equal to 1, suppose. Then 0 to 1 x dx. This is actually half, right? But
It will not work.
yes, so those two are not working. Using this example, it is clear those two will not hold, because mod of fx square, this is actually 1/4, half, and sorry, c is working in this case, right? C is working, but D is not working using this counter example. So we need to, this is counter example for D. But what about counter example of C? Can it produce something? So instead of 1, let us take fx equal to x and c. So for C, let us take fx equal to x. In this case, 0 to 1 x times fx, that is x squared dx. This is actually 1/3, and but
1 by 9. It will work. No, it will not work.
mod of fx square, which is same as, what is the value of,
1 by 3.
it is also 1/3. So it is actually already calculated, so this will not work. But what about if we take something like x square? So then this will become x times x square, which is x cube. So this is 1/4. But mod of fx, what is mod fx squared dx? That is 0 to 1 x to the power 4 dx. This is actually 1/5. So its root,
It will not work.
is it working? This is actually x to the power 1/5.
Not working. So 1 by, we will get 1 by 40, sir.
Sorry, it is 1 by root 5. This side is actually 1 by 4 root 5, and this side is 1 by 4. So this is correct, right? This is not working. Means this is a counter example. So okay, this is actually done. Even that is also working actually. That previous thing, if we just put x here, this is also working because we need to divide it by 4. So those are actually counter example for this. Okay.
Sir, we have to take square root 2, sir. Square root of 4.
Yes, sorry, 2 root 5. But then also it is working. Because it is already greater than 4. 2 root 5 is greater than 4. So it is okay. So this C and D are not correct. It is not correct because of those counter examples. So this is actually enough. Okay. This counter example is enough for those two cases.
Sir, there is 3 also, sir, na, sir? 1 by 3 we have to multiply by 1 by 3, sir. So it will become 1 by 15, sir.
Where 1 by 3?
But we have also na x, sir.
Yes, this is okay, and this is also
Sir,
okay.
you have taken for, sir, this is fx, and we have, sir, x also, na, sir.
Yes.
So we have to multiply by 1 by 3 also, sir, because we are considering the inner product of, sir, x comma x square.
Yes, so x comma x square means x cube, and if you just integrate, you will get
We need to take, sir, norm, sir. Norm of fx and norm of x, sir. So we basically we need, sir, need to calculate norm of x times norm of x square, sir. So norm of x square you are getting, sir, 1 by root 5, and norm of x is we have, sir, previously calculated 1 by under root 3, sir. So it will give 1 by under root 15. And also, sir, this is not correct, sir. Norm of fx when you take, so it will be you will be getting, sir, x to the power 4. Yes, sir. This is correct, sir.
This is actually correct. I have
Yes, sir. This is correct, but we have to multiply by, sir, 1 by root 3, sir.
okay. If some
For whole thing.
constant thing is there, then just multiply. Otherwise, just check with this example. Yes, this should hold actually.
No, sir. I am saying that we want to calculate, sir, norm of f into norm of g, sir. So
Yes.
you are only considering norm of fx, sir.
No, I am not doing that actually. I am because I am not doing that norm fx times norm gx. I am using that thing, that is left hand side is this and right hand side is this by 4, right? So I have taken that part.
Okay, sir. Okay, sir. Okay, sir.
So this is correct actually.
Okay, sir. Okay, sir.
Okay, so this is question 9 and now question 10. So this is also we need to calculate here. What is the question? Here's the vector space.
Option A, sir. Option
With
is correct.
okay, let us see if those are correct or not. And this is the definition of the this is the notation inner product, and we need to see if those inner product can be written as those kind of combination. So first thing is to observe that inner product of this thing is actually distributed into two parts. One is real part of this inner product plus I times imaginary part of inner products. This is true for any number. So any
Yes, sir. Option B is also
complex
correct.
number, yes. So any complex number can be written as real part, z equal to a plus ib. So it can be written as real part plus I times imaginary part. So option C is correct, right?
Yes, sir.
Now let us see what other options are correct or not. So again, also note that if we just, so those are some observation. I times z, if we just multiply with I, then it will be IA minus B. So what is the real part of IZ? Real part of
Minus
IZ.
B.
Yes. But that is same as imaginary part of Z, right? Imaginary
Minus
part of
times.
Z, yes. Just put minus. And similarly, imaginary part of IZ, this is actually same as A. So
Real object.
this is real object. So those are some observation we need here. And so if we just see what is those, so let us write right hand side. For example, for option A, we just check what is I times real alpha comma I beta. So using the property of inner product, so let us see this. So this is same as take conjugation of the second part and multiply with real alpha comma beta. But conjugation of the second part, it is
Sir,
same.
real. Sir, there is real na also, sir.
Okay, sorry.
How can you take I conjugate outside?
Alpha comma I beta is same as minus I times alpha beta. So from here, real of alpha comma I beta, that is same as real of this part minus I alpha beta, but real of IZ is same as minus of imaginary Z. So this is same as minus of imaginary Z.
So there is minus I, sir.
This is same as plus imaginary alpha beta. Right? So from here it is clear that real alpha beta plus I times. So from here this is clear that real alpha beta plus I times real alpha plus I.
Alpha I beta.
By this is same as real alpha beta plus I times, we have already
Imaginary.
calculated, this is real alpha comma I beta is same as I comma alpha beta. So using that equation star, we obtain this is same as I imaginary alpha beta. So again this is true, right? Because we know that alpha beta can be written as this. So this is actually same as alpha beta. So this option is correct.
Option is correct. Yes, sir.
Now we need to see the option B. So I alpha times beta. We need to see what is I alpha times beta. So I alpha times beta, this inner product, this is again same.
Real of sir alpha beta.
Yes. So I is same, and we need to see what is imaginary. So if we just apply imaginary,
So we'll get real of alpha beta.
yes, this is same as real alpha. So this again this is true, right? So this is real alpha beta, and second is I times imaginary alpha beta, which is the same.
Yes, correct.
So this is correct. Now what about
Last one is not correct.
why this is not correct?
Because we should write it real alpha I beta.
Yes. So let
By A.
so instead of checking this, we need, it is enough to produce a counter example. So if you take alpha equal to I, beta equal to I, then what is alpha times beta? This is same as I times I bar, right?
Sir, A and D will be equal if the thing imaginary part will be equal, sir. So each real alpha beta is equal to real alpha I beta.
What is
We
the
can see
problem?
also from here, na sir.
Where is the issue?
Sir, by A and D, sir. In option A, alpha beta is written as this, and by D, this is written as this. So two complex number are equal if real and imaginary parts are equal, sir.
Yes, yes, this is.
So both thing will be equal if imaginary part of alpha beta equal to imaginary part in A, sir. So we will get sir real alpha beta is equal to real alpha I beta, sir.
Yes.
But this is not the case, sir.
Yes, you can check. Yes, this is whatever you are suggesting. This is actually true. That if we just check those, there will be no. Maybe there is no.
We don't need a counter example, but you can also prove that from
Yes,
using.
imaginary parts are not same actually.
Yes, sir.
So that is the issue. Because so let us check that part. So if we write I times real alpha, so imaginary I alpha comma beta, so it is already calculated. Imaginary I alpha comma beta, this is real alpha beta. So real part is already same. There is no issue. But I times real alpha beta. So this is the imaginary part, but this should be same as this, which is not correct, right? So from here, you can conclude.
Yes, sir.
But you can also produce a counter example like this. So inner product of I comma I, this is actually 1, but if you put I comma I here, so what is imaginary part of I alpha comma B? So this is what is imaginary part of I alpha comma beta? This is I comma I times I comma I, which is minus 1 times minus I plus I, and similarly I times real alpha beta. Sorry, yes, so it is imaginary. So real of alpha beta means real II, which is again inner product of II means actually 1. So this is again I. So we can see that sum of those two things, it is actually 2I, but it is actually 1. So those are not same. So these incorrect, since those two are not same. Okay. So let us see this question. Here Y is non-zero vector, and we need to see which of the following are subspace of V. Okay. So if we start with the first condition, it is given that is the subspace W is defined to be all X belongs to V which are perpendicular to the to Y, right? X is perpendicular, that is X and Y are orthogonal. So we need to check if W is a subspace. So suppose X1 and X2 two element belongs to W. So X1, X2 belongs to W, and
Sir, this is orthogonal complement of Y, na?
yes, this is orthogonal complement of Y. You are right, but let us check. And C belongs to the field F. So we need to check that linear combination of those two.
Alpha X1 plus X2 belongs to W or not?
Yes,
So 0 is already there because inner
so
product.
it's already there. 0 comma Y.
Yes.
So inner product with 0 is always 0. So 0 belongs to W. Now let us see x1 x2 belongs to W means inner product with Y equal to 0, right? Now we need to check cx1 plus x2 if this belongs to W or not. So let us take inner
By
product with Y.
linearity of the inner product in first component.
Yes. So by homogeneity and those distribution property, this is same as cx1 comma y plus x2 comma y. Right. So, but x1 comma y, this inner product is actually 0, and x2 comma y is also 0. So those two are 0. So their sum is 0. Therefore, W is a subspace. So option 1 is correct. Now what about option 2?
Not correct.
Why not correct?
0 is not there.
Yes. For 2, we can see 0 does not belong to W. So this is W2. 0 does not belong to W2. Why? Because 0 comma y, this cannot be, this is always 0, which is not equal to 1. So 0 does not satisfy this condition. So 0 cannot be in W. Therefore, W2 is not a subspace. Not a subspace. So this is false. What about option 3? So yes.
Not correct.
So let us see if it is correct or not. So now the condition is more complicated.
Sir, if we take any non-zero element such that inner product xy is 0, but inner product xx non-zero because x is non-zero.
Okay. So it is given that W3, that condition is all x such that inner product with z is 0 for all z which satisfies the property z comma that fixed vector is actually 0. This inner product is 0. So 0 is already there because we can see 0 satisfies this property, right? Whatever z is given, 0 times z is always 0. So 0 is there. So let us try to prove if it is inner product or not and see where is the problem. So let, similar to the previous thing, x1 and x2 belongs to W3. And similarly see, so let us check individually. So x1 plus x2, so x1 similarly C belongs to F. So we
Sir,
need
I think it is true, I think.
yes, so let us see. We need to check if this inner product is 0 or not. So we know that this is true, right? X1,
Yes, sir.
X2, those are belongs to W3. This means Xi times Z
Z will be 0.
0 for
Yes, sir.
all Z
This is correct.
satisfy those certain conditions. So that means by same reason Cx1 times Z plus X2 times Z. So those are 0, right? Those are 0 by this. So this is 0 for all z satisfying this condition. So this is their sum is also 0, satisfying for all z satisfying that same condition. That is z inner product y is 0. So from here it is clear that W3 is a subspace. Right? So what is happening here? It is actually x times z equal to 0, but z satisfying this condition means z, it means actually take all x which satisfy the condition x is orthogonal to that orthogonal complement of z. So x is orthogonal to this vector space.
Sir, union actually. Sir,
It,
union of subspaces, na sir?
yes, it means
All those Z which are in orthogonal complement of Y, then
yes,
find the orthogonal complement of those elements, then take union.
we don't need to take union.
Why, sir? Sir, actually, this is the same thing, na sir?
Yes, orthogonal complement is actually a subspace. We'll prove it later. It is actually very easy to show those orthogonal complement is always. So here we are using those kind of thing. Actually, we'll see what is orthogonal complement. But here the essentially the fact is that in general orthogonal complement of any subspace, this is actually a subspace.
No, no, sir. I am saying that this W3 is sir, a subspace defined as for those union of those elements which are union of orthogonal complement of those elements which are in orthogonal complement of Y.
Yes. Absolutely, that is the W3. So W3, it is actually take orthogonal complement of something generated by Y, that subspace, and take another orthogonal complement. That is actually W3. So all those are actually subspace.
Again, this is Y
Yes.
generated by Y, sir.
that is absolutely same, because we'll see later that taking double orthogonal complement will give the same thing actually. So it is
Sir, can we see it from here without that result, sir?
huh?
Sir, can we see from here without that result that this is actually, sir, subspace generated by Y?
Without this result, yes, you can see that this is actually how can it be seen? Maybe we cannot see it directly from this result. This argument only prove that this is the subspace, but to see that this will be actually generated by Y, we need to prove this result actually. Orthogonal, taking double orthogonal complement will give the same thing.
By that procedure, can we not show that, sir?
Yes, the exactly same procedure, whatever is used to prove that fact, will be used there.
First, we show, sir, W3 subspace of, sir, Y.
Actually, you need to prove this thing actually. Any vector space can be written as W direct sum that orthogonal complement. Exactly that proof will give. That is taking again, if we take the orthogonal complement of W, so instead of W, if we write W per, then this can be written as this. From here you can conclude that those two, W and W double per, those are actually isomorphic. Those are isomorphic. Okay. So those are actually not for now. Maybe we'll see it later. So let us take
Okay,
a
sir.
look. So certainly option D is 3 is correct, but option 4 is false by the same reason. 0 does not belong to this space. The same reason. Okay. So let us see next question. So T is a polynomial from 0, 1 to R, and so V is vector space of all such linear polynomials. So given V is vector space of all polynomial which is a function from 0, 1 to R. Right. Now Tx is defined by this polynomial, and the inner product of any two things, it is the same inner product as we have previously seen. Just multiply Px with Qx and integrate from 0 to 1. Now we need to find a orthogonal basis for these polynomials actually. So actually it is polynomial whose degree with degree less equal to 1. It is already given that all polynomials will look like this kind of thing. So degree of this polynomial is given less equal to 1. So what can be done? So initially it is easy to observe that everything, this vector space is spanned
Sir,
by,
second and third.
yes. So if we choose alpha 1 equal to 1 and alpha 2 equal to x, this gives a basis for this vector space V. Now we need to find orthonormal. So again we will use Gram-Schmidt method, and we'll find beta 1 and beta 2. So beta 1 is same as alpha 1, and what is beta 2? So beta 1 is 1, and beta 2 is same as alpha 2 minus alpha 2 inner product with beta 1 norm beta 1 square into beta 1. So alpha 2 means x minus, so let us calculate those two things. So what about norm of beta 1 square? This is same as 0 to 1 beta 1
Sir, third option is correct.
Yes. So it is alpha 1 is 1. So we need to put there. So it is 1 times 1 dx, which is same as 1. And alpha 2 inner product beta 1. So what is alpha 2? Alpha 2 is same as x. So x times beta 1, which is 1 dx. So x square by 2.
Sir, it is not given na, with respect to what we are going to find this orthonormal basis, sir. So we
Yes.
only need to check the if it is orthonormal, normal or orthogonal, sir, both,
Yes, yes. That
and
is
also linearly independent.
correct. That is exactly correct. But let us try to find an orthonormal basis first. So this is actually x minus half of beta 1. Beta 1 means 1. So x minus half. So those two will give me a orthonormal basis, but we need to check norm of beta 2. What is norm of beta 2? Because those are actually orthogonal, but we need to check if those are orthonormal or not. That is norm, or what is the norm? So let us find the norm. So norm of beta 2 square is same as this, which is x minus half cube by 3, 0 to 1, which is 1/3 time cube minus
Plus 1 by 2 cube.
yes. Again, putting 0 will get plus
Minus 1 by 2 cube. So this is yes, sir.
no, there is some mistake, right? X minus, this should not be 0.
Sir, there is plus, sir. Plus 1 by 2 cube, sir. First term. Because
First,
1 minus 1 by 2 is 1 by 2 simply, sir.
yes. So it is 1 by 12 actually, right?
Sir, it can be 0, na, sir.
1 by 8, 1 by 24, 1 by 4, 1 by 12 actually.
Sir, it can be, sir, 0, na, sir. It can be 0, sir. Is it necessary that?
No, those two will be because those two, if it is 0, then beta 1 and beta 2 are not a basis. Gram-Schmidt, whatever Gram-Schmidt orthogonalization gives, this forms a basis for the same space.
Sir, norm of a vector is 0 if and only if it is a 0 vector. Right?
Yes. So
Yes.
it cannot be 0.
Yes.
So we need to divide it by, so therefore a orthonormal basis, an orthonormal basis, it is beta 1 by norm of beta 1, similarly beta 2 by norm of beta 2. So norm of beta 1 is actually 1, we have already proved.
1 comma
1 by square root
the
12.
root. Yes.
So those are two orthonormal bases, but actually this is not matching with anything, right? So from here, no, it is actually matching. This is actually 2x minus 1 by,
By, sir, C. It is magic with C. 2 root 3.
oh sorry, it is divided by 1 by root 12. So it is root 12 will be on the above. So that is square root 3 into 2x minus 1. So this matches with this answer, and so we are lucky that we found the correct thing. But now,
Sir, it is easy to check, na, sir. By, sir, simply options.
yes,
Check if it is, sir. First,
in this question, it is better to check by options, because whatever we, those kind of basis actually dependent on the choice of those 1 and x. If you choose another thing, you may get another orthonormal basis. So that is actually problematic part. So if you check with other things, then you can prove that those are actually not orthonormal. For example, we have already seen that norm of x is actually not 1. Right? For example, what is norm of x? This is 1/3. X squared, just integrate x squared, which will give 1/3. Square root of 1/3. So this is incorrect. And now here, if you just norm is okay, but if you just integrate, that will not give you 0. That is not 0. So inner product of those two things is not 0. Those are not orthogonal. Similarly here, that is okay, but norm of x minus half, that is norm of x minus half is actually 1/12. So those are not correct because that is not orthonormal. That is orthogonal but not orthonormal. So option 4 is incorrect. Option 3 is only correct answer. Okay. Now, okay, thanks. So now let us check next question, 13. Here is n by n matrix and inner product of x comma y. It is defined as, we don't know if it is inner product or not, but something like this. It is defined as inner product of ax comma ay with respect to that Rn, and this is something new thing, and we need to check when this will be an inner product. So this
Sir, 1
phenomenon,
and 2 and 3 and 4.
yes. So
Non-negative, no, sir. In non-negative case, we can take 0, no, sir.
yes. So let us check if those are.
Sir, A can be, sir, A can be considered as a linear transformation, sir. Like
Yes.
previously we have defined, sir, inner product xy is equal to tx,
Yes.
ty.
So let us prove that fact actually. Here we need to see a fact. So this is inner product. When this will be inner product? So we need to check those kind of property. That is, first one is homogeneity. So everything is over real number. So x plus x dash comma y. This is same as, by definition, this is same as ax
So
plus
this
x.
is always true, sir.
Yes. So let us see. So ax plus ax dash comma ay, but this is same as, by definition, this is same ax inner product in real number. By definition of this is same as this distribution. We can separate like this, and
Inner product xy plus inner product x dash y.
by using this definition, this is same as inner product of xy plus inner product of x dash y. And similarly, if you just multiply with some element, you can easily prove cx comma ya, that property is also holding.
Sir, all the properties of inner product will hold, sir.
Yes.
Like the distributive property and like these are there.
So all those property will hold.
Yes, sir.
Similarly,
We
you can,
only need to check positive definiteness.
yes. So similarly, you can check on the other component, that is uh, x comma, just reverse those roles, and those will be also satisfied. So we only need to check those positivity condition, that is uh, inner product of two things is greater equal to 0, and 0 if and only if. So this is inner product of two things, this is 0, greater or equal to 0, and 0 if and only if x is 0. So we need to check those two properties. So first one is clear, right? Inner product of ax comma ax, by definition we know this is defined as, so recall that on Rn, what is the inner product on Rn? How do we define inner product on Rn?
x1 y1 summation x1 xi yy.
Yes. So inner product of those two things is same as sum of those components xi yi, where x is same as x1 up to xn. And now you can check this is actually same as if you write x as, so what is, okay, maybe let us write x as this kind of component, because of our, otherwise multiplication will not be defined, because A is n by n matrix, so you need to take n as column, x as column. So the inner product is defined by this definition, but this is actually same as x transpose time y, right? So if we use this definition of inner product in Rn, this is actually same as transpose of the first thing times the second. But this is same as x transpose A transpose, and this is Ax. Right. Now, can we conclude something from here? Oh, sorry. This is not needed actually. From here, we know whatever y we choose. So let z equal to ax itself. Then we always know z transpose z. This is always greater or equal to 0, right? It is always true. This is same as norm of z square. So this is always greater or equal to 0. So the first property is okay. So this is holding. Now we need to see the second property. So the second property means ax comma ax, this is 0 if and only if x transpose times ax equal to 0. But this is actually same as if and only if norm of x square is 0. But this is if and only if x equal to 0, right? This norm is norm in Rn, that is inner product of x with itself. But what is the condition for ax equal to 0?
X belongs to nullity of A.
When this condition is equivalent to x equal to 0, this is true if and only if given A is invertible. Otherwise, this is not true. So we need to, one side is always true. X equal to 0 will means Ax equal to 0. But for the reverse part, we need A is invertible. Otherwise, the x equal to 0 need not imply x equal to 0. So it is clear that A should be invertible.
Sir, Ax is equal to 0, this will imply x is equal to 0. How are you getting this condition?
When this condition holds, x equal to 0 imply x equal to 0. When will it hold?
Sir, A can be also 0, no sir?
Then x equal to 0 will not imply x equal to 0, right? For example, if you take a equal to 0, then choose any non-zero thing.
Yes, sir. So how can you deducing this x is equal to 0?
Okay, I am telling here that x equal to 0 if and only if x equal to 0 is only true. This is only true when only true if and only if A is invertible. Because suppose A is not invertible, then what will be the problem? A is invertible means rank of A is non-zero, then there exists some x for which A times x, there is some nullity, right? So there exists some non-zero x for which, so if A is not invertible, then there exists some non-zero for which Ax equal to 0.
So, sir, basically we are assuming the conditions of inner product space, then we are deducing things from that condition.
No, I am not assuming this. I am telling we need to see this thing is 0. We need to prove this is 0. So let me tell it in another way. So we need to prove that one side is always true. So we need to see x comma x, this inner product, when this inner product 0, it should imply, this is not inner product, but this should 0 imply x equal to 0. We need to, so
Yes,
which
sir.
condition is needed for this thing? So we are proving that this x comma x equal to 0, this will imply x equal to 0. This will only true when A is invertible. If A is
Yes,
invertible, those will be true.
but
If not,
if not,
then this is not true, because we always, there exists x which is non-zero for which Ax equal to 0. So
yes, sir.
that property,
That is what I am telling you. Na, that we are assuming the inner conditions of inner product, then we are deriving the condition for A. For
yes,
which condition
yes.
will be true?
We are we are seeing that what is the problem, what is the obstruction for this.
Yes, yes, sir.
So we are just we are writing all those conditions and we are checking where is the issue. So we found the only issue occurs here. X equal to 0 if
Yes,
and
sir.
if x equal to 0. So for this implication, so this implication is not true. This implication is on. This is only true.
Only A is invertible. Yes,
Is it okay?
correct, sir.
Okay. So we see those are actually true. Rank of A equal to n. Invertible if and only if.
Kernel A is 0.
Yes. So
Single.
nullity is 0. Kernel A is 0. And
Third and fourth need not be true.
yes. So
They
for
can
4,
be positive always as no negative eigenvalues.
for 4 non-negative eigenvalue, whatever you can choose any non-invertible matrix such that its eigenvalue is positive.
Take any diagonal matrix containing some negative eigenvalues, containing some positive eigenvalues. Then these third and fourth will be incorrect, sir.
Yes. So maybe let us see what are the counter example for those two things. So let us produce counter example. So all eigenvalues are positive. So determinant should be 0. Maybe put 1 0 and 1 0. So those, what are those eigenvalues?
So eigenvalues are only 1 and 0. Sir, this is not the case, sir. Sir, it is simply saying that the inner defines inner product if and only all eigenvalues of A are positive. Sir, if we can give some matrix whose eigenvalues are some positive and negative, then this will not hold.
Yes. So this will give a counter example for option 4, right? Here we can see all eigenvalues are
Yes,
non-negative.
sir. Yes, sir.
1 and 0, those are
But there
eigen.
should be -1. Sir, -1 there should be. Because he is saying non-negative. Okay, so non-negative means 0 and positive.
Yes, 0 and
Okay.
positive.
Yes, sir, yes.
So that satisfies the
This will work.
condition, but
This is not invertible.
A is not invertible because 0 is already eigenvalue. So
Correct.
this is incorrect because we already know that this will be inner product if and only if A is invertible. So that option 4 is incorrect actually. And what about third thing? All eigenvalues of A are positive. So can we
Not.
prove something?
Yes, sir. Take a diagonal matrix whose eigenvalues are positive and negative as well.
So eigenvalues are positive will imply this fact, but the converse may not be true, right? Because
Yes,
this
sir.
will imply this is inner product, because eigenvalues positive means
A
non-invertible,
is invertible. Yes, sir.
but the converse is not true. For example, take minus I, take a equal to minus y. This is for counter example for uh, yes,
Yes, sir. Correct, sir.
counter for 4,
This will work.
counter for 3, because the condition, the given condition is if and only if. So we see that this is an inner product, but eigenvalues are not actually positive. Both eigenvalues are minus 1. Okay, okay, Sandeep. So let me stop here. I don't have any other problems. So if you have some doubt, you can ask.
Sir, there is one topic, sir. Applications of sir inner product space. Sorry, sir.
Yes, application of inner product space.
Sir,
Yes,
applications of primary decomposition theorem, sir. There is one section also, sir. You have not taken any problem from that section, sir.
okay, maybe I will include some problem in the next tutorial.
So that is very good, sir. Thing, sir. I think in
Okay.
this week, sir. Applications of primary decomposition theorem.
Yes, yes. Okay. Have you seen those Jordan canonical tutorial?
Yes, sir.
Okay, nice. So maybe I don't have any other problem. Maybe we can solve few other problem, because
Sir, I have a problem from the net. Can you ask here, sir?
what is the question?
Sir, let me see, sir. Sir, if A belongs to sir M and R, such that rank of A to the power n square is 0.
Rank of,
A to the power n square is 0.
you have said P.
A, sir, A.
Oh, A belongs to MNR and rank of A to the
A
power
n square is 0.
A
A to the
square.
n square. A to the power n square.
A to the power n square equal to 0.
Yes, sir.
Means it is 0 actually.
Why?
Rank of something is 0 means it is 0, right?
Rank A to the power n square is 0 actually, na?
Means it imply A to the power n square equal to 0.
Yes.
Then what is the question?
The which of the following is equivalent to saying that A has n linearly independent eigenvectors? So the
Oh,
options are A to the power n is equal to 0,
n linearly independent eigenvalue,
vectors.
eigenvectors,
Yes, sir.
if condition 1 is A to the power n
N
equal
is 0.
to, yes,
A to the power n square is 0.
A to
A
the
is
power,
equal, A is equal to 0. A square is 0.
A equal to 0 and
A square is 0.
okay. So it is given that a to the power this is already given.
Yes, sir.
So if A is 0, then there is n linearly independent eigenvectors, right?
Yes, sir. This is correct. Yes,
This
sir.
option is correct. Now, what about A square equal to 0 will imply? A square equal to 0. So, all of those are actually nilpotent operators. Now, given A square equal to 0, it means Jordan blocks will be like this. So, the maximum size of Jordan blocks are actually 2, right? And all those diagonal entries will be 0. Now, okay.
Sir, if A is 0 matrix, then it has, sir, n linearly independent eigenvectors.
Yes. So this is not true because you can take this counter example 0, 1, 0, 0. So it is 2 by 2 matrix. So for example, take n equal to 2 and consider this example. So it satisfies the criteria A square equal to 0, but it has only one eigenvector, right?
Only one eigenvector.
Yes. Because eigenvalue is 0, and what are the eigenvector? With respect, you can see that rank of this matrix is 1. So what about nullity? Nullity will be also 1. So there is only one eigenvector.
So rank is 1, then nullity will be, sir, n minus 1. Na?
No, I am taking n to be n equal to 2 and consider this example.
Okay, sir.
So this is not true, and similarly this will be also not true by the same fact. So only option 3 is correct, and rest of the options are actually wrong.
Sir, a zero operator has, sir, n linearly independent eigenvectors.
Yes, only nilpotent operator which has n linearly independent eigenvectors, that is actually 0.
0, yes, sir. That because
Otherwise,
then it will be diagonalizable.
yes. Otherwise, there exists some Jordan block, and for that part, we don't have enough eigenvectors.
Yes, sir.
You can interpret in that way. Otherwise, you can prove also this.
Sir, there is one more question, sir.
Okay.
That if the characteristic polynomial is given x cube times x minus 5 square.
X cube chi x, that characteristic polynomial is x cube into
X minus 5 whole square.
x minus 5 whole square. Yes.
Sir, and minimal polynomial is given as x square times x minus 5.
X square into
Minus 5.
yes. Those are new questions.
So, sir, we need to show that T bar induce, sir, linear operator, sir. T bar such that V upon null T minus 5i.
Nullity of t minus kernel of t minus 5 by like
Yes, sir, yes, sir.
P by kernel of t minus 5 by
2 V by kernel of T minus 5i, sir.
okay, that question is already solved in previous tutorial.
Yes, sir. Sir, which one, sir? In which week, sir?
Just previous tutorial. You can use the Jordan form and deduce this.
Okay, sir, you have solved it.
Yes, it is. The solution is already there. If you have further problem, you can ask.
Oh, okay, sir. Okay, sir. Thank you, sir.
Actually, you need to just see what you can. It is actually five degree operator, right? Means the dimension of vector space is 5. It is already there. from here it is there. So
Yes, sir.
you can obtain the
JC form.
Jordan form of this, and
Yes,
from
sir.
here you can calculate. That is already there. You can just look at the previous tutorial.
And one question is also relating to this, sir. V upon if we replace kernel of t minus 5I by kernel of t, sir.
Kernel of T. Yes,
Yes, sir.
that question.
That is also there, sir.
Yes, that problem is already solved in previous tutorial. You just look. You can already determine from here what is the matrix, and from there you just calculate those facts.
Sir, if any sir inner product is defined like sir inner product of sir x1 x2 comma y1 y2 is equal to x1 y1 plus 2x1 y2 plus 2x2 y1, sir, then sir how can we check that this is inner product or not, sir? Let's say it has sir so many terms, sir. So then checking the conditions will be sir cumbersome if there is sir.
Whatever you are telling, it is true. Those kind of quadratic for those kind of combination, inner checking those if those are inner product or not, it is really hard. But we'll see later. There is a chapter which called quadratic form. Using
Yes,
that, the bilinear form. So those kind of thing is actually x transpose p is of y.
yes, sir.
And if p has some nice form, nice quadratic, p is obtained from nice quadratic form, then it is easy to check. Actually, that is called actually positive definite.
Yes, sir.
In that case, those are actually inner product. Otherwise, no.
Yes,
Okay,
sir. Sir has mentioned sir about quadratic forms are there, sir.
yes.
In this week, sir.
It is not for this week because it is in the last, maybe in the last tutorial, bilinear forms.
In week 11.
Maybe in week after inner product, maybe week 11 or 12.
Okay, sir. So these are some advanced topics, sir. In
Yes,
algebra.
those are some advanced topic. And also that Jordan canonical form, that is also some non-trivial. Before that, everything are easier.
Yes,
Right?
sir.
But
Yes.
Jordan canonical form, that is first, that is minimal polynomial, and Jordan canonical form, those things
And
are
sir, primary decomposition theorem is sir
yes.
also sir some
That is
advanced.
also some non-trivial thing. It is it requires some knowledge actually. Otherwise, it is hard to see.
So sir, will we sir study about sir orthogonal subspaces in detail, sir? Because there are more questions from these topics, sir. Nowadays, sir.
Yes, in the next, maybe in the next tutorial, we will see some special kind of operator which is called normal operator, and for normal operator you can actually diagonalize. So that is why those are actually important. In particular, you know that uh, those kind of thing, symmetric, skew symmetric, orthogonal, all those are actually diagonalizable. So in the
Yes,
next
sir.
tutorial, we'll see those kind of things: normal operator, unitary operator, those kind of things.
Yes, sir. Okay, sir. Thank you, sir.
Okay, so let me stop here. Thank you.